Alright, Mr. Claxton's Algebra 2, Algebra 1, that is, again. I keep saying Algebra 2. I guess I've made more videos for Algebra 2 than the other classes. This is the example that I shaded earlier. I would like you to know that I shaded all the way up to where this black line should intersect that dashed green line there. So I should extend that black line so it does intersect. That way you can see that that feasible region that I've bubbled in right here goes all the way up to that intersection point. Yes, we could calculate that intersection point if we wanted to be exact about it. We would just treat these like equations over here. We would replace the inequality symbols with equality symbols, and we could use we could use graphing to estimate, or we could use substitution or elimination to get that exact point. That point that I'm going to go ahead and mark in yellow. Okay, if you can see it there. Highlight that point, that intersection point. And that point is just an estimate right now, because I was not extremely exact, although probably as exact as I could be when graphing that line. Okay, so moving on now, the second example that I want you to check here involves two systems. Involves one system made up of two inequalities. We've got inequality 1, linear inequality 1 in blue, linear inequality 2 in green. Notice how I had to flip the sign here. I had to flip the sign because you see in my work right down here that I had to divide by a negative. And when you multiply or divide by a negative, what must you do? Flip it. You got it. So I flipped it down here, and I transferred that up there, wanted to highlight that in red. Okay, I graphed linear inequality 1 by using the y-intercept, which was 0, -3, which I plotted right here, and then I followed the slope. Just like Toucan Sam follows his nose, I follow the slope to make a line. So that's up to right 1, up to right 1, up to right 1, up to right 1. We keep going up to right 1 forever. That's what that little arrow means on the end of that line. Okay, that's why we have that constant rate. Slope is that rate of change. I could also go down to left 1, because -2 over -1, you know that's a positive. So down to left 1, down to left 1. And again, they're going to come to this common intersection point. Okay, somewhere about there. I know that's just an estimation right now. That is just an estimation. Okay, I could be exact with that, but that's just an estimation. So my feasible region here that I've shaded in is the intersection of both linear inequality 1 and linear inequality 2. I guess just to make that more apparent, I'll go ahead and color that in a different color so you can kind of see that this right here, this region that I'm coloring in magenta, right? I've got the blue line below, that blue inequality. Actually, it's not, it is a line, but, and then I've got the green solid line above. So this is that region, goes all the way down to, right? If I could pick a point out of there and test it, I know that it would give me a true system over here. I would plug it into both 1 and 2. So an easy one to do is actually 0, 0 to see if my region is somewhat accurate. So we're going to go ahead and test 0, 0 here real quick. Now I'm going to show you how to do that. So we take the test point. I'm going to go ahead and grab a different color here. This is a test. Okay, this is only a test. All right, and I'm going to plug in a 0 for x and a 0 for y. Now I'm going to go ahead and rewrite that. 2 times 0 minus 0. Well, is that, I always like to draw a question mark because I'm not sure yet. Is that less than 3? We could take 1/3 And now I'm going to multiply it times the y value, which, oh, that's 0. Is that less than or equal to 0 plus 1/3? So let's go ahead and see if both of these check out. 2 times 0 is 0. 0 minus 0 is 0. Is 0 less than 3? Yes, that checks out. 1/3 times 0 is 0. Is 0 less than or equal to 0 plus 1/3? So is 0 less than or equal to 1/3? Well, yes it is. And I know that the point 0, 0 lies within that shaded, that feasible region, right? That intersection of both of those linear inequalities. So, boy, I've done a pretty good job there. I know I've done a pretty good job. So my test point right there, I know that it's going to make 2 true statements. Okay, moving on now. I didn't explain how I graphed the green one, but I'm pretty sure that you could do it the same way. Okay, you could do it the same way by locating the y-intercept and following the slope. Okay, and you can follow that slope for as long as you want to. The next example that I wanted to show you, and a lot of people are getting this wrong. Many people are getting this wrong. In that, I really would like to use substitution here. Okay, I use substitution, and the reason why substitution makes sense for this. Let's go ahead and go back one. I don't like the way that worked. Trying to draw grouping symbols there. Here, that's a little better. Okay, I take that, I plug it into the equation below. Because I'm multiplying that entire red quantity times 2, I get rid of that fraction, okay? Because really, these just cancel out, right? And I'm left with a minus 3x plus 8. I got to consider that that's like saying a negative 2 times a negative 4. I get 3x minus 3x, which is 0. My x's are now gone. I'm left with a statement of 8 equals 20, right? 0 plus 8, which is 8, equals 20. I know that's not true. That's a false statement. So that means no solution and an inconsistent system. Okay? This is the only time that you'll have no solution and an inconsistent system. This means that the lines are 2 parallel lines. They're 2 parallel lines. They run parallel to each other. I'm not going to make you graph them. We're not going to make your mind go through that mental anguish tonight. So I know the lines are parallel. They'll never intersect. Okay? And because they'll never intersect, there is no common point. There's no meeting point between them. Whenever you get a true statement, this is what a lot of people are missing. Whenever you get a true statement, such as 0 equals 0, that is always true. That will have many solutions. Many. In fact, an infinite amount of solutions. And because of that, we say that it's a consistent system because there are solutions, you see. But it depends which one you're talking about. Because those 2 lines lie on top of each other. So, it's a consistent, dependent system, right, with an infinite amount of solutions. All right. Hopefully that's been helpful to you. This is Mr. Claxon signing off for how to graph systems of linear inequalities and how to solve a system of equations.